point to initial responses of body systems to exercise. Ventilation is the volume of air breathed out of the lungs in 1 minute. You can find out the ventilation of a person by using the equation ventilation equals breathing rate times tidal volume. Breathing rate is the amount of breaths that we take per minute, and tidal volume is the volume of air expelled in one breath. Ventilation increases as the muscles have a higher demand for oxygen. This means that for these changes to happen, our heart rate and stroke volume values must increase. At rest, our breathing rate is low at around 12 to 15 breaths per minute. However, during moderate exercise, these values increase slightly from around 28 to 32 breaths a minute due to the higher demand for oxygen around the body. Then, during maximal exercise, these values increase rapidly to 40 to 60 breaths per minute because of the oxygen depth in the muscles and an even higher demand for oxygen. Like breathing rate, your tidal volume values must increase in order to expel as much waste products as can, such as carbon dioxide, in order to maintain a high standard of performance. Resting values for stroke volume is about 500 milliliters, then during exercise these values increase to 1,500 milliliters, although during maximal exercises these values can reach up to 3,000 to 4,000 milliliters. The increase in tidal volume and breathing rate means that there is an increase in ventilation because of their functions. We can work out the values of ventilation by multiplying the breathing rate by the stroke volume. This means that at rest, the ventilation will be around 6 liters. During moderate exercises, these values will be around 42 to 48 liters, and during maximal exercises, these levels will be around 120 to 240 liters of air per minute. The increase in values is because of the increased demand for oxygen and to remove the waste products more quickly. This means that the performer can sustain the level they're working at for a prolonged time. We recently performed 2 tests to measure the effects of different types of exercise on our breathing rate, heart rate, lactate levels, and blood pressure. We also rated perceived exertion and skin temperature. We performed 2 tests, one aerobic and one anaerobic, and one anaerobic to see how the body would react to different types of exercise. The first test was the multi-stage fitness test up to the end of level 8, and the next test was a 20-second sprint cycle Wingate test. The multi-stage fitness test requires the person to run between a distance of 20 meters over a period of time, which decreases each time they run the distance. Before we start the multi-stage fitness test, our breathing rate will be around our resting value, although it may increase due to an anticipatory rise. This is where anxiety or adrenaline causes a rise in heart rate and therefore breathing rate. From our results, we can see that our pre-test athlete had a breathing rate of 12 breaths per minute, showing no anticipatory rise, although our level 2 reading has increased to 25 due to a higher demand for oxygen in the muscles. This high demand for oxygen is picked up by the chemoreceptors in the blood, which then alert the respiratory control center of these changes. The respiratory control center then tells the brain and therefore the body that there needs to be an increase in tidal volume and breathing rate in order to keep up with the oxygen demand. This graph shows a positive correlation between the breathing rate and the multi-stage fitness test, so as one increases, as does the other. This is because the harder we work, the more carbon dioxide we produce in our muscles. This also leads to a higher increase in oxygen demand. From our graph, we can see that our post-test results show that our athlete is working at or near his maximum level. Due to the increase of breathing rate during the multi-stage fitness test, the athlete's ventilation value must have increased, as the equation shows that as one value increases, the other values will also increase. We also completed another test called the Wingate test, which is where an athlete works at their maximum level for 20 seconds. For our Wingate test, we had our performer do a 20-second sprint cycle. We measured their breathing rate before the test, which was 17, therefore showing an anticipatory rise. Due to the activity being anaerobic, the breathing rate may also increase slightly during exercise, but will mainly increase post-event. Our graph shows a big increase between the breathing rate values of the pre-test and the post-test. We can see that our performer's breathing rate is Our graph shows a big increase between the breathing rate values of the pre-test and the post-test. We can see that our performer's breathing rate is in the maximum stage of exercise, meaning that there's a high amounts of carbon dioxide and lactic acid in the muscles, which can only be reduced by the increase of oxygen. This increase in breathing rate and demand for oxygen will also mean that the performer will breathe deeper into their lungs, meaning that tidal volume will also increase. Due to the rapid increase of both breathing rate and tidal volume, the values for ventilation will also increase. This graph is what you would expect to see your breathing rate look like during any exercise. It shows a steady rapid increase followed by a slightly less rapid increase until it reaches the maximum. Then the breathing rate slowly lowers back down to resting levels. We would also expect to see similar results for stroke volume and ventilation. Lastly, this graph is called the spirometer trace, which is a graph that shows all volumes of the lungs. In exercise, we would expect to see the tidal volume increase and the expiratory reserve and inspiratory reserve to decrease. We would also see that the vital capacity of the lungs increases and the residual volume would decrease. In a game of netball, players' breathing rates vary in different stages of the game. For a centre player, their breathing rate will rapidly increase at the start of the game as they need to travel and move into space. Their breathing rate and therefore ventilation levels will remain high throughout the game because they're always busy. However, for a goal shooter, their breathing rate will only increase when their team has possession of the ball. This is as it is in play in the end of the third quarter. When the player is moving into space or throwing the ball, the player's breathing rate will rapidly increase and will stay high whilst their team has the ball. When their team shoots or has lost possession of the ball, the goal shooter's breathing rate will begin to decrease because they are no longer creating carbon dioxide at such a high rate, and the demand for oxygen is decreasing as the oxygen debt in the muscles has also decreased. The goal shooter's heart rate will continue like this the goal shooter's breathing rate will continue like this until the game ends. For inspiration during exercise, the external intercostal muscles and diaphragm contract, and the accessory muscles are the pectoralis minor and the scalenes. This moves the ribs up and out further than inspiratory at rest. This creates a greater increase in lung volume, meaning that a steeper gradient is created, and air enters the lungs at a faster rate. However, during exercise, both the internal and external intercostal muscles contract, as well as the latissimus dorsi and abdominals, which are the accessory muscles. This forces the ribs to move further in and down that expiration at rest, and the diaphragm relaxes and goes back to its dome shape. This means that there's a greater decrease in lung volume, leading to a higher pressure of air inside the lungs compared to outside, so air is forced out. The Herring-Brewer reflex is a reflex that stops the lungs from overinflating. Stretch receptors are found on the bronchi and the bronchioles to respond to large stretches of the lungs. The expiratory control center sends impulses to the muscles to control the breathing. The VALSALVA maneuver is a type of breathing that increases the pressure in your thorax without expelling any air. To perform this, you must try to expel air whilst holding your nose and keeping your mouth shut. It can be used in many contact sports to prevent any injury as it creates resistance and braces the athlete for impact. For example, in rugby, when a member of the opposing team runs at you to tackle the performer, they will perform the VALSALVA maneuver to brace the impact of the tackle. This helps to prevent injury. Muscle contractions of the abdominals and the pectoralis and trapezius muscles help to create this maneuver.